In this session, we're going to cover the basic concepts and definitions about statistics. So what we will cover here, we will first start with an introduction. Then we will introduce the definition of variable, what is a variable, and variable types. Then we will talk about the frequency distributions. Then we will take a look at what is sample and what is population, and continue with the descriptive sample statistics and parameters, which is very important. And in order to manipulate them, we do some data encoding for easing statistical calculations. And we will also cover some, again, very efficient methods for calculating the mean and standard deviation. And finally, we will talk about coefficient of variance. Again, a very important concept for scientific studies. Okay. So, statistics studies on methods for gathering, analysis, and interpretation of data. All of them are very important. We gather data, then we analyze it, then we try to put some meaning on it. What is it for, or to answer the question, why is something happening, or how, whatever. And statistics is required for objective decision making as well. Otherwise, if you're not talking based on data, it means that you're making your claims in a subjective way. And statistics helps us to talk based on data, and it is required for objective decision making as well. You see a simple scientific study here, the World Fertility Survey. Like it underlines or emphasizes some trends about how the parents having children has changed. It's analyzing the trends on it. How is it going up or is it going down based on data, for example. You can see many studies like this in medicine, in whatever domain you like. You say finance and social studies, whatever, okay? Because it is the basis of science and objective decision making anyhow. So what is a variable? It is an observation of a measurement. Okay. It can be weight or, for example, your height. So you need a tool for this measurement. Okay, maybe you need a device, for example, making for that measurement, usually. And a variable can also be a count. I mean, you count the number of, for example, customers waiting in a queue. It is also possible. It becomes a count. Or a variable can be a categorization as well. Okay, this person is male and this person is female, for example. You categorize them based on their sex, for example. Or maybe colors. Okay, this is a blue stone, this is a, for example, red stone, and another red stone, and a yellow stone, whatever. Okay. So we can have basically three types of variables, and based on how we achieve those data. And if the observation results could be depicted by probabilistic functions as well, so maybe it can change over time in different domains. So those are now named as random variables because they can change. They're subject to change. The events that you can expect different outcomes even on identical conditions as well. I mean, it's very interesting, right? Suppose that you give a blood sample at a for example, a hospital or something like this, and the moment you give your blood sample, let's say it's 10 o'clock or something like this. Just 5 minutes later, give another blood sample, but they will not be identical results, right? It can change. Let's say, the person taking it can be same as well, but the needles reach can be different. At that moment, the blood passing there at that time can be a little bit different. Even for the same person and even on identical conditions, you can expect different measurements. This is what we call random variables now. Just imagine that there would be no difference on observations. Then what would be the need for statistics anyway? It means that there will be no need for statistics, because if you make this measurement over and over again and get the same results, there will be no need for statistics anyway on the population. For example, a capital Y can be used for representing the weight of a block, for example, each block. So it becomes a variable now. And in the bottom states that, for example, this is your fifth measurement, which is 200 kilograms. It is the result of your fifth observation on a population, for example, on a set of data. And the fourth one, for example, 201 kilograms. And let's say sixth one can be 205 kilograms. It can happen anyway. So now let's take a look at variable types and based on their nature this time, okay? Variable types can be categorized based on their nature as well. There are continuous variables, for example, weight or height. Can you say that my weight is exactly this real number or something like this? Or my height is exactly this much? No, it's not possible. It is based on the sensitivity of the measurement instrument, which transforms it into a discrete variable. That's possible. For example, if you have a weight measurement device at home, maybe its sensitivity can be up to kilograms. That's it. But if you have a more sensitive device, you can make measurements with the sensitivity of the grams than milligrams, for example. So you can, there is no limit to this, and these types of variables are called continuous variables. And how about the discrete variables? Discrete variables strictly cannot take any value between two integers. It's not possible. So for example, the number of rotten apples in a basket. Can you say that we have 100.5 rotten apples in a basket? No, it's not possible. It's either 1 or 2. Or the number of decayed teeth in your mouth, for example. Okay, you can have 3 decayed teeth, for example, but you cannot have 2.5 decayed teeth. Yeah, it's not possible, you see? So you can say that these are discrete variables. And there are also categorical variables, which are pretty interesting because you cannot measure or even count them. For example, the degree of pain. The doctor asks you if you have, for example, stomach ache or headache or something. When you go to a hospital, the practitioner will ask you, can you tell me the degree of your pain? You try to describe it, like it's high, low, or something like this. You can also transform the continuous variables into categorical variables as well. The people who have this type of, for example, body mass index can be categorized as thin or obese or normal, whatever. So then again, it becomes a categorical variable, but with some transformation on the continuous variable. And you can also transform the discrete variable sets as well into categorical variables. For example, the olives, you categorize them based on their quality, top quality olive, fair quality olive. You see it on the markets, for example, depending on their size, for example. So it become a categorical variable. And variable types can be categorized again in a different manner as well, this time not based on their nature, but based on their scale, how they get measured. The nominal scale is definitely strictly qualitative. They have separate categories in it and each of the categories correspond to those categorical variables. For example, the condition of a product. Is it working or is it broken? Is it old or is it new? Is it long or, let's say, is it short or whatever? Okay. And the ordinal scale is addressing where degree of quality is important here. Now you can rank them. There is a logical ordering here. For example, the degree of pain. If you maybe, rank it between 1 and 10, for example. Okay, the degree of pain, And there is also interval scale where information about how far data pairs are from each other. Now this one becomes quantitative. These are more likely qualitative, but now we are in the domain of quantitative variables which are based on strict measurements, right? So here the interesting point is there is no real zero reference point here. These type of variables are called interval scale variables, and you can transform between the interval scales. That's possible. However, you have no idea about the ratio between the data pairs. Only the distance between them is meaningful. That's it. For example, IQ. For example, temperature, right? For example, suppose that my IQ is, let's say, 100, okay? And your IQ is, for example, let's say 150. Does that mean you are, let's say, 50% more intelligent than me? No, you cannot say this because you don't have a real zero reference point here. Or temperature, for example. Suppose that today it is, let's say, 5 degrees Celsius in Izmir, for example, and it is supposed that -5 degrees Celsius in Ankara, for example, okay? So does that mean Izmir is twice as hot, or let's say 5 times as hot than Ankara? Is it possible? No, because there is no real reference point as well. And you can transform between the interval scales. For example, you can go from Fahrenheit to degrees Celsius or vice versa. You can also make transformations between scales. That's possible. This is called the interval scale. And finally, the last one is the ratio scale, which is also called the Stevenson scale. Now we're talking about an absolute 0 point, which is your starting point, and it becomes comparison between them can be much more meaningful. Suppose that I'm 60 kilograms and let's say a horse is 120 kilograms. I can say that the horse is twice the weight of mine. So, and the number of women in a classroom, for example. Okay, in classroom A, the number of women are, let's say 9, and in classroom B, the number of women are at 3. We can say that we have 3 times more women in class A than B. So we're talking about a variable which is based on ratio scale here. The transformation between scales is really possible, but with a cost, with loss of information. So you can go from here like this, but you lose information. It's possible. You can make transformation between the scales of variable type. Okay, now we have an idea about the variables and variable types. Now we can continue with the frequency distributions. We're trying to understand the data gathered. So why do we use frequency distributions? For organizing and summarizing the gathered data. That's the main idea. It works pretty well for discrete and categorical data. Like let's just imagine the number of, for example, decayed teeth. Number of decayed teeth, and for example, in a health scan between the children, for example, and the frequency of those, let's say, occurrings, and you can say that it can be either 0, 1, 2, 3, 4, and okay, more than 4, for example. Okay, these are your frequency distribution for this. And let's say that suppose that you have seen 3 students like this, 7 students like this, 6 students like this, let's say 3 students like this, 1 student like this, and people who have, or children who have 5 or more decayed teeth in their mouth is 0, let's say, and you have 20 samples here, and these are your, this would be your frequency distribution here. That's the idea. Or suppose that you're working with, this was an example for discrete data, or suppose that you're asking people about their smoking habits. Okay, smoking habits, right? This time, this is a categorical data, and the frequency here, and let's say smokes, and say quit, the people who quit smoking, and the people who never smoked, for example. Now we have 3 different categories, right? I mean, you cannot say one is, far from the other one. It's not possible. It's categorical data, and you write the frequencies here, and you can see that it is 150 samples, for example. See, again, I summarized all my data. It's pretty useful for understanding what is going on. So that's the main idea about frequency distributions. Okay, for discrete and categorical data, it's more or less like this, but it is relatively harder for continuous data because of its say complexity. Suppose that you have a data set like this. Now look, of course it's still let's say we're talking about integers, but it becomes somewhat continuous, right, due to our understanding. Here we have 156 patients here, and they use a drug which drops their serum cholesterol levels. Okay, they're inventing a drug like this, and this is their test data, for example, and they measure their serum cholesterol levels before and after taking the drug. Okay, and then if it is, for example, dropped by, let's say, 12 points, for example, you mark it as minus 12. Or if it is raised for, let's say, 17, you write it as positive 17 or something like this, and they get their data now. Now, the thing is, again, you need to summarize it like we did here before, like discrete or categorical data. How can we do it? So, again, we need a mechanism for this. We need to make some understandable categories between, look, like this. We will define some categories here and write the frequencies here and try to summarize this type of data. But we have some rule of thumbs to take into consideration. One of them is comprehension thing. Instead of choosing, let's say, 7 or 8 between the classes, between the categories, you can go ahead and use some rounder numbers, like more understandable, human-friendly numbers here, like categories of 10 or 20 or something like this, or 5 maybe, okay? More, easier to comprehend categories. And you need to cover, of course, this is the most important thing maybe, cover whole range of data. You need to do something like this. You shouldn't leave, your categories should not leave some of the data out. Then it would be, again, not meaningful. We should avoid sparse categories to a degree. We use Bolton method for this. Like your 50% of least frequent categories must cover at least 10% of your whole data. We will check whether this one holds for our example or not. And we should have equal range on each category for easing for future calculations. You first have, let's say, a category like this, then you have a category like this, for example. So then here it is 10, then here it is 20. So again, it's not very practical for calculations later, right? Now let's take a look if our categorized data fits these categories or not. Okay, and we first check whether the let's say categories are given in a let's say easy to comprehend manner. You see, it's very nice. So it's tens, right? With 10, and is it always 10? Yes, it's always 10 here. You see, there are no different range on different categories. So we can say that this one and this one holds here. So, and did we cover whole range of data? Yes. So you can see that your maximum number is here is, for example, the 50 something. Let me see if I can find it. It's not easy, but I had checked this before. Okay, you have here 55, for example, this one. See? And you have some up to minus what? Minus 100, right? Up to minus 100, for example. So this one is, again, these are your lower limit and upper limits. They're all identified here. They fit somewhere here. And then you put the frequencies here like this. Sometimes I mark like this, sometimes I mark like this, I count like this. It depends on your liking, how you do it, how it's comfortable for you. But the author, my professor, again, preferred it like this. So here you can see the frequency here, and this is the total number of samples. When you add all of them up, you will get the total samples. Okay, can you see that? Can we see that it is also satisfying the Bolton methods check here? Let's see. Just pick the how many categories do we have here? Just identify it and identify 50% of them later. Least membered categories. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 categories you have here, right? And 50% of them are what? 50% of them are 8 categories. 8 categories that have least number of members in it, or least frequency in it. Okay, this one, the 2, 3, 4, 5, 6, 7, 8, 9. Oops. Not 9. 8 is enough, right? 1, 2, 3, 4, 5, 6, 7, 8, right? This one, the least members categories, this one and these ones, okay? And let's just try to add them up. It's 12 and then 14, and here you have 9 and 10, 24 members here, and like we have 24, is it right? You have here 10, and this one is 11. No, it's 13, I'm sorry. This one is 13, right? 11 here and 2 is here. So you have 23 over how many you have in total? 158, and it corresponds to roughly 15% of all data. So does this satisfy? More than 10% of all data? Yes. So it also satisfied the Bolton methods categorization as well. As you see, now you can, summarize this type of continuous data like this efficiently, but it requires a bit of expertise. It's normal. When you're categorizing, 2K has proposed a method which is called stem and leaf table in 1974 for not losing the original value of the data. See here, we are losing some value, right? Suppose that you have a data which is particularly minus 25, right? Minus 25. Where is it? Minus 25 is located here, right? Here. But which one is minus 25? Okay, you cannot understand here. Or suppose that all of these data here is minus 21 or minus 29. Okay, 21 or 29. It may be a bit different understanding, right? You have no details here. So for this sense, if you want to put details here, you just put their first number here. For example, for this one, you put this one here as category, for example, but this one as detail, for example. That's it. This is called stem and leaf table. Okay, stem and leaf table. This is how we use the stem and leaf table to avoid losing the original value or original data, because it is important to have the original data. Here the sensitivity of leaves are also important, because suppose that you have some like more data like this. Let me try to show you here in my notes, for example. Let me just give one example to you from the textbook again, from our textbook. Okay, suppose that you have these data, this one, this one, this one, this one, and this one, and so on. Okay, you have lots of data like this. Now, when you're trying to summarize this, you just write, okay, the first digits, for example, they're all equal and going like this. Okay, oops, not 12, of course. After 10, here comes 11. Okay, and it goes like this. And you write the leaves here as the 10th like sensitivity here. These will become your leaves, right? These will become your leaves, and its sensitivity is in tens. You need to write this as well, how sensitive it is. It is a tens digit, because that's why. And you write the leaves like this. And let's see, oops, I'm sorry, not this one, of course. Like you will have here 6, and you will have 6 again, and you will have here for 10 2 and 3 here, and then for 11 you will have here 5, right? This is how we build the stem and leaf table here. What happened to these data here? These, let's say, extra information, they're lost. They're lost, okay? But it's still better than this one, okay? A bit more sensitive. But be careful here. You need to keep in mind that be careful about the sensitivity let's say level here. You need to put it, don't just be careful. Suppose that your data was something like this. 9.72 and 8. Now it would you can easily say that now, okay, you will again have a stem like this, like 8, 9, 10, blah blah blah, goes like this, but now your leaves will be what? Here, right? Like your leaves will be in 0.1 sensitivity, right? So then you will write them, okay, for 8 it's 6 and 6 and so on. Okay, but now this time it is 0.1 sensitivity. You need to identify this. Okay, this is the idea about the stem and leaf table and the sensitivity of leaves. Okay, now the cumulative frequency distribution is also useful, particularly for comparing different experiments. For example, A and B drugs done with different samples, for example, and different sample sizes. Suppose that you have conducted experiment A with this much of people in Izmir, for example, and you in Ege University, for example, medical faculty, but you conduct another experiment of this drug in, for example, 𝐩𝐥𝐚𝐲𝐛𝐚𝐜 University medical faculty in Ankara, for example, with suppose that 250 sample or patients, for example. Now you can compare them if you have a cumulative frequency distribution. Otherwise, it would not be very meaningful if you summarize like this, right? For 15 people, 250 people here, you will have more, lines here, but not give an idea for comparison. It will not give an idea for comparison. What we have here is, here are our categories again. We have 16 categories, right? The same thing. And this is middle value of each category given here, like middle value of each category, and their frequencies given here, the same, okay, up to here, maybe this one and this one, everything is the same, right? And this is your frequency ratio. This is your frequency ratio here. Suppose that I have only one sample here. What is the value of it in my total data here? I write it here, and it corresponds to 0.64%. See? 0.64%. And how about, for example, this one? For example, this category, it has 22 in it. 22 frequency in it over 156. It corresponds to, let's say, like approximately 14%. That's the idea. Here, you also do the, cumulative frequency here, which is interesting. Cumulative frequency here. Okay, you add them up now. Okay, 1, 1, 0, still 1. Plus 1, now it becomes 2. Plus 5, now it becomes 5. Plus 6, now it becomes up to 100 and, let's see, 56. That's it. Now it is the cumulative frequency here, and it is the cumulative frequency ratio here. What you see here is its ratio. As you see up to here, you covered, so for example, with 94 samples, you cover approximately 60% of whole data, and it is dropping the cholesterol level. This is how you try to reach some conclusions for comparing. And up to now, for example, in another experiment, if you say that it is, let's say, 50 something percent, you can say that roughly, but it's not, I mean, I cannot say this directly, but basically, okay, drug A is maybe more efficient than drug B for dropping serum cholesterol levels. Maybe, of course, I cannot say it like this directly, but only from this data, but I need to make other tests. We will see them in detail in chapter 4, hopefully. But that's the idea with cumulative frequency distributions. Now, there are also graphical distributions. So far, we only filled some tables. We can use bar graphs for discrete variables and histograms for continuous variables. You can also combine the upper edges of histogram bars for achieving the envelope of the frequency distribution as well. Here you see an example of a bar graph that we just discussed about the decayed teeth of people in a classroom, like or children in a classroom. You remember this one, right? What was the values, if we remember from our example? Where did I put it? I couldn't remember directly, but it was okay. Now I found it. Okay, it was. This one was okay. It was 3 and 7 and 6. This one, and this again, the 3, and this is 1. Okay. This was the example that we have given for frequency tables, right? The discrete frequency tables. And you can also summarize this in a bar graph. That's possible. And how about this one? This one is, we just discussed the cholesterol levels of patients. Here you see the middle values of each category here given. You see those are the middle values. Okay, you put the middle values here. How we get them? It's easy. I mean, just you take the middle value of the maximum and minimum level in that category. So you have here 9 difference between them, and you go 4.5 from the left hand side and 4.5 from the right hand side, and you meet here, right? This is your middle value for each category. That's how we write that. And you write their corresponding frequencies here. You see, it's pretty easy. And finally, you can connect those dots to have the envelope of this distribution, which would look like really continuous distribution. You see, which would look like a continuous distribution. In fact, this is how we do it. Okay, now let's solve an example together from the scratch with you. Okay, I need a fresh board. Now, suppose that this is the example 1.6 from your textbook. 1.6, problem 1.6 from your textbook. And we have 30 students in a classroom, who have been asked to solve a math problem. They have been asked to solve a math problem, and we record in how many seconds they answer this problem. Okay, we made record all those values. We first measure, okay, and they are, let's say, this one, 48, 54, 43, 51, 53, 43, 1, 2, 3, 4, 5, 6, 7, 8, 41, 63. Okay, then 45, 38, 46, 46, 49, 42, 48, 46, 44, and 52. And we go on, 43 and 47 and 58 and 65 and 45 and 44 and 68 and 48 and 72 and 57. Okay, you have your, okay, 30 measurements, 30 seconds. Okay, their units are all seconds. And there is a hint here in the question that tells us that the first class should be this one. Okay, so this is your hint, and there should be 8 classes. These are your hints. If you don't have a hint, be careful. If you don't have an hint, you need to take what into consideration. Don't forget, we are glad that the author gave us a hint, but if you don't have an hint, don't lose hope. Just be careful about these rule of thumbs, and be careful about them, and you can also summarize it on yourself without a need for a hint. It is based on your practice, or if you do it a lot, if you solve lots of examples, you won't need any more hints. Okay, let's do it with the given hint. Now we will have those 8 categories as given as this, or let's say seconds here, seconds. This is our first category, 40, 44. Look, they should be equal, right? The differences should be equal. 4, 55, 59. You also solve it yourself. It's fun. And okay, here I have my 8 categories. All right, so good. And now I need to have their frequencies put here, right? So the ones between okay, we have what between, let's take a look at the first category, and how many do we have there? Okay, I think we only have one here, this one, right? So its frequency is let's say 1. And then between 40 and 44, you will have which ones? 40 and 44. Let's say 1, 2, 3, 4, 5, 6, and 7, right? So you have here 7. And between 45 and 49, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10, and 11, right? So you will have 11 here, and between 50 and 54, how many you have? Now let's use another color. 50 and 54. 1, 2, 3, 4. Oh, that's it. Okay, you have 4 here, and between 55 and 59, between 55 and 59, you have 1 and 2. 2 here. Between 60 and 64, between 60 and 64, you have 1 and 2 again. You have 2 again. And between 65 and 69, have 1 and 2 again. And between 70 and 74, okay, only 1 left, I guess. This one. So this is your one. When you add all of these up, let's check, double check. You have here 18, you have here, and oops, did I make any mistakes? Is it 18? No, it's not 18. It's, I think this is 19. Okay. So this one is what? It is 10. And okay, this one is 1. And here you have 30 samples, right? Great. So, I mean, now you can depict this as a histogram, right? You can have this as a histogram, you can draw this here on an XY axis. Let's do it together, right? You have, how many categories did you have? 8, right? 1, 2, 3, 4, 5, 6, 7, and 8. And what's the range of frequency here? From 11 to 1, right? From 11 to 1. So I say right here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So all looks good. Now, do you think this one satisfies Bolton property as well? Can we do it? Can we check it? This is extra, okay? We're doing it for extra Bolton check, okay? Let's do some Bolton check here. The Bolton check says 50% of the categories, half of the categories should cover more than 10% of data. The least half of the categories, of course. Which are they? This one, 1. 4 categories I need. 2, 3, and 4, right? Either this one or this one, it doesn't matter. And it is what? How many samples in it? 6, right? And my total is what? 30. And my ratio is what? 1/5. Just 20%. Is 20% more than 10%? Yes, so it satisfies our Bolton check or Bolton criteria as well. Good hint, okay? So they gave us, the author gave us a good hint. So let's write their, middle values here. Be careful, we need to write the middle values here. What are they? It is 37, the middle values, 42, okay, goes like this. Let's write them. 37, 42, goes by 5, like 47, 52, 57, 62, 67, 72. Okay, these are my middle values here. And what else? I need to correspond them in their locations. Like I need to, for the first category, I only have a single. This one. Okay, here I have this one. And for the next one, I have 7, right? Okay, let me write them too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Okay. For the next one, I need to have like going like this. it should be going like this. Okay, this one. Okay, and for the next one, I need to have 11, right? It's going like this. I need to have 11. No, it's not writing. Oops, I'm sorry. I need to have 11. I need to have 11. Okay, this one is this one. I need to have 11 here. This point, this point, this point, and then 4, 2, 2, 2, 1. 4, 4, 2, 2, 2, and finally 1 you have here. Okay, when you write their corresponding positions here, like this one, okay, you fit them like okay, you fit them like this, and these are your histograms. Okay, when you combine the top points here, you will end up with your envelope as well. That's the idea. Okay, so this is what we're talking about, the histograms, example 2. Okay, now what is sample and population? When we talk about a population, we're talking about a group of units requiring inspection, research, and interpretation based on one or more variables. So we're curious, we should be curious about that population particularly. When we say population here, it has a broad cover with respect to its biological definition. So when we say population here, it can be a population of chairs produced in a particular factory, for example. Not only the population of living organisms or something like this. It has a more broad cover in statistics. That's the idea. So there are two main aspects of the population. What is the population we're dealing with, and what are the observation variables that we are concerned with? For example, your population can be 20-year-old male athletes, and the observation variable can be their blood serum leukocyte levels, for example. Okay, that's one example. Or we can talk about screws manufactured in a particular factory. Now this becomes our population, and the length of those screws. So that's another example. That's the idea. Two types of populations with respect to size of the group are possible. There are finite populations. They're also known as real populations, that you're capable of understanding how many people in it. And there are also infinite populations. They're also known as hypothetic populations, where you can only dream or estimate about the total number of population. That's the idea. Whatever the population we're dealing with, usually we have troubles in considering all units when we're trying to work with that population, understand that population. Why? Because you cannot reach. Just imagine you're making a survey about the elections, for example, in Turkey or something like this. If you can ask all the valid people who can vote, let's assume that we have 40 million, for example. If you ask 40 million, then, I mean, it could be, yes, good, I mean, sampling of the population, but it's impossible. So we always work with small examples taken from that population. How you take those samples to represent that population is within the scope of a whole other, I mean, expertise, which is called sampling theory. It must be good. So your samples should reflect the population. Otherwise, it can be biased, what you predict about the population. And what do we mean by the parameter? Parameter defines a quantitative property of a population. We're talking about something which can be measured numerically. Okay. For example, if we return to our 20-year-old male athletes and their leukocyte mean, so that defines that population's leukocyte mean. That's the idea. The parameter's real values unknown. I mean, it's impossible to know. It's impossible to have. It's not practical to have 40 million samples. What you do is trying to predict it. As a researcher, you do this. Try to predict it with respect to the samples you take. This is called sample statistics. The methodology after collecting samples, what you do for analysis is that's also must be good. The statistics, what you're doing here, and our parameters about population are depicted by Greek letters. Don't forget, we will see this distinction. While sample statistics are depicted by Latin letters. That's the difference about the population parameters and sample statistics variables. Okay. And parameter, in fact, is a constant value, which is real because it represents all units mean, for example. So it is a constant value. It is the absolute truth, that it is the ideal condition, ideal dream that you're searching for. But practically, it's not easy. And sample mean can vary from one sample set to another. Okay, you take a group of let's say 10,000 people and ask them about their, I mean, voting tendencies to some, so it will just represent an approximation to real parameters. If you take another sample of, let's say, 1,000 people, for example, then it can vary. I mean, those sample means can vary one from another. But does population parameter vary from, I mean, time to time or something? No, because you're considering all the members in that population here, so it is constant. The idea is like this. So, statistics, right? Statistics, okay, this is extra. Statistics is crucial for defining population properties by predicting population parameter by means of calculating sample statistics. We're trying to predict those parameters. That's what we're doing by statistics. For that purpose, we rely on descriptive sample statistics that define the population. What we're doing is summarizing the observation data by means of scientific methods. This is very important. The observed data should be summarized by means of specific scientific methods. Otherwise, what would happen? Just make a guess, pause the video. It would be subjective, right? We're trying to be objective here. So far we have seen table-based summarization, right? Just a few slides back, and we talked about this and solved examples, and we know about graph-based summarization. Now we take one more step ahead, and we'll talk about numerical summarization as well. It is also called descriptive sample statistics. We're working on both on x-axis here. We're talking about numerical values on the x-axis. There are some location-based measures and difference-based measures. Let's see them one by one. The first one is the mean. It can be, I mean, there are different ones like geometric and harmonic and weighted mean as well, but let's start with the arithmetic mean. What we have here is just the most popular one here. It's something like this. So suppose that you have four gas samples and their oxygen level in it, levels in them, and you record them. For example, like this is like 14.9%, like and 10.8%, and 12.3%, and 23.3%. Okay, these are your samples, and so when you're saying about the mean of them, you add them up, like, and you will eventually get this number, and divide it by the number of samples here, and you will reach a result here, which is called your arithmetic mean, right? And of course, it should be percentage as well. You can extend this approach or generalize this with this formula, of course, like this, from the first sample to the nth sample, the last one. What you do here is this operation. That's it, and it goes like this, right? So that's the idea about arithmetic mean. And if we want to, add up or exclude the first observation, for example, or something like this, we can start from, let's say, the second observation. You can also tweak this like this, but it's very rare. Almost we never do this because we always take all our samples into consideration. That's the idea. The representation of this arithmetic mean is the mean of the population is can be different. You also depict them like this, from I1 to N. See, it's a little bit different, but meaning the same thing. XI, I'm sorry, this one also should be I, right? Okay, good. And this one also means the same thing. These are all different representations because you take all of the samples into consideration. And also this one, we are talking about the same thing all the time. See, you have N samples, and finally this one. This one is also the same thing. And if you have a variable called X, and its arithmetic mean is denoted with this one, okay? If you have a variable X here, and this would be your arithmetic mean in this case. And so your arithmetic mean is calculated like this, not surprisingly. You add all of them and divide it by n, right? So this is your arithmetic mean. Normally, this arithmetic mean corresponds to usually, the center of weight of your observation, and it might be different from the observations you have. So when we took the example here, look, my observations are this one, this one, this one, this one. That's it. I have 4. But my arithmetic mean is something different. You see, it's not in this set, right? It's not a real observation. So this is the case for arithmetic mean. Your mean can be out of this set. That's possible. And if some of the values repeat for a few times, you can use this formula for easily calculating the arithmetic mean like this, based on their frequencies from I, xi, fi. You see? Now, how many times a particular observation gets repeated is done here, and this is the number of your total observations, which corresponds to n, right? So that's the idea. Okay, let's solve an example about this. So suppose that in a newborn clinic, let's say 10 babies born one day has been born a single day. What is their weight average? Okay, let's say the arithmetic mean of their weight, for example. You take the values into consideration here. Let's write them from our textbook. 3, 3, 4, 4, 3, 2, 2, 2. That's it. That's all our data. And we have only three different, you see, three different weights here. Okay, the first one is 2 kilograms, the second one is 3 kilograms, and the last one, the third one, is 4 kilograms. And they also have their own frequencies, right? How many 2 kilogram babies we have? You see, 1, 2, 3. Okay. And how many 3 kilogram babies we have? 1, 2, 3, 4, right? Good. And how many 4 kilogram babies we have here? F3 equals C, 1, 2, 3. So this is, now, as we have this, it's easy to calculate the arithmetic mean here, which would be directly something like this. X equals 1 over Fi, as we discussed, and I, Xi, Fi, that's it. So when you put these, pretty straightforward, and when you add them up, and it's also in the question, you have n as 10 here, and 2 times 3 plus 3 times 4 plus 4 times 3, coming from this table, right? You multiply them, and of course you need to have a calculator, and the result is 3 kilograms, which would be your arithmetic mean. So we do this frequently as well, and we'll see this approach often in our next examples as well. So this was all about the arithmetic mean. Okay, we also have other means for which are the geometric mean and harmonic mean. The geometric mean is the taking the logarithm of the logarithms of all the data. Now let's take a look at this. So and converting it back, of course, with antilog. So let's see it from the example from the text as well. So your geometric mean is the antilogarithm of the summation of the logarithms of your data. That's the idea. So, and in order to, other than dealing with the algorithms and taking the antilogarithm back, it's more practically something like this. Your geometric mean is multiplying all of your data, then taking the nth root of that result. So So it is depicted like this. You can easily summarize this or show this in a more general form like this. Okay, this would be corresponding to the same thing, 2 up to xn. And there are also different, again, representations for particularly this one. Okay, this means also the same thing, not surprisingly, just like the arithmetic mean, jargon, xi, for example. And also this one, we're talking about always the same thing here. So they are equal to each other, and also this one. Okay, we can show them like either this way, this way, this way, or this way. They're all same. So your geometric mean can be can be defined like the nth root of your px, and also this one. Okay, x nth root of n. That's it. So this is about the the geometric mean. And the other one is harmonic mean. Harmonic mean is represented like this: 1 over hx equals 1 over n 1 over x. Now you see you're just adding these 1 over samples to get the summation here, and it looks like this. So you first calculate this, then take the inverse, multiplicative inverse, and reach your harmonic mean. So if we do this with the same set of examples here, with the oxygen levels here, if we do this on the same set of examples, what will we have? Let's take a look. So your data set, of course, it's pretty simple, but that's the idea. Your data set was this 9. This is the first one. Your second data was this one. Oxygen levels in those gas samples, right? Our example was something like this. These are your data. Okay, these are your data, and your geometric mean will look like this. So it is you multiply all of them, like times. It's fourth root, right? Since we have 4 samples, and the result will be 14.65%. And what is the harmonic mean of those data? It would be directly written like this. Harmonic mean is 1 over 4 times 1 over plus 1 over 32, 3. See, when you do this calculation, you will take a harmonic mean out of it, and your harmonic mean, your harmonic mean would look like this. Okay. So you need a calculator. You will definitely need a calculator while practicing on your own in the exams, and also while doing your homework. That's it. And look, this one was your geometric mean, and this one was your harmonic mean. And what was your arithmetic mean? You remember? Your arithmetic mean was, what was it? It was, where is it? This one, 15,325. 15,325. Okay, arithmetic mean is 15 3 2 3 2 5. Okay, this was your arithmetic mean. So your x is it's better if we denote it like this. It has a symbol anyway, so we can use it, or hx. It is called this is much better if we represent it like this. It's hx, and it would be much better if we say that this one's name is gx. Good. Okay, these are very nice. Okay, x, and this is how we will solve the questions in the exam as well, and gx. So if you use the same set of samples, you will see that your x mean, arithmetic mean is more than, higher than your geometric mean, which would be higher than your harmonic mean. We usually rely on arithmetic mean in our daily examples, but some type of populations show different distributions. They can show some skewed distributions, and you have to be forced to use geometric mean and harmonic mean in those cases to represent those populations practically or in a much better way. Okay, now let's continue with what? Okay, we're finished about this one and this one as well, and now we go to weighted mean, the student's favorite, right? The weighted mean that you are already expert with, and when you calculate your cumulatives, right? I think you're already familiar with this. So this time we're giving weights to some particular measurements in the data set. So it is called the weighted average x. We see this one denoted by this symbol, and it is I from I to n ai x. Sorry, weight of I xi over I1 to n, the total number of weights, like the frequencies. Okay, so this is your number of observations in this for your observations, and the one is their weights, and this is showing their corresponding weights. Now let's make a simple table here with the courses and their credit and their your grade, or whatever your result from that course. So you will have, for example, physics here, physics and math, and statistics, for example. Okay, statistics, and their credits are different, and your grades are also different from each of them. And how will you have this? It's easy, right? You can just use this approach for calculating the weighted mean here. It's just 5 times 60, just all of them, plus 3 times 70. You just give the corresponding weights, and finally they are divided by what? The weights, total weights. Okay, this is how we do it, and the result will be what? 11, and it should be your weighted mean. It look like this. This is your weighted average from, or your cumulative from all those grades. If you had calculated them directly without considering the credits here, you would end up with x equals this, and you can easily see that this one is a much more better representation of your cumulative here, other than this one, because this has more detail in it. That's the idea. Okay, now we also have other location measures, and median is next. Now let's take a look at what median is. I have a fresh board for this. Okay, the median is the middle value when you sort all of your data. Let me give you an example from the textbook, so it would be much more easier to explain this. Suppose that this is your data set where you have this one. So if you have something like this, you first sort them, okay, from smallest to oops, I made a mistake, right? Smallest to highest value is, and you go from here, and you go from here. If your total number of samples in your data is an odd number, the middle value would be your median value. Okay. If you have more than, if you have even number of let's say observations here, okay, this is another sample set, for example, this one. It is already ordered, so don't worry. Now you start going from here and here. It means that those two would be decisive on your median value, and you will take the arithmetic mean of these two values and get the result, this one, as your median value. So as you see, your median value might not be included in your original data set as well. If you have an odd number, it's pretty straightforward, it's the middle value. And if you have even number of samples, you take the two samples in the middle and take the arithmetic mean of them, and that's the idea. These can be useful for example, if you have some outlier or extreme values in your data sets. For example, suppose that you have a data like this and a data like this here. Maybe your distribution can be skewed to either side. In this case, you can focus on the more common samples here, sample values here. In that type of data set, median can be more explanatory. And you can see that median, if this is your data set, median splits this data set into two equal parts. There are also other popular terms for this. Maybe you will remember them. It's not the only one. If you divide them in four, for example, like this is in four different pieces. Maybe you remember this. It is called a quartile, right? And this is median, this is quartile. And if you, let's say, divide this data set into 10, you see, say this is your middle point, and you will have 5 here and 5 here, okay, which is called the decile. you will have decile measure here, and if you okay, maybe you remember this one much better, and you split here to 50 pieces, and in 50 parts here as well. What is this called? Let's pause the video and think about it. It is called percentile, right? Percentile. And they all can be useful in different type of data set. That's the idea. Okay, so we're done with median as well. And what is mod? The last, our last location measure. It's pretty straightforward. It is called the most repeating, value in a data set. For example, let me try to use an already available example. Okay, what is your mod in this data set? Your, top repeating sample here, this one, see? Your 19 is your mod here. And do you have any other mods that we can cheat from? Other, from our other examples. Let's see, we can cheat from other examples. This one, no, I cannot cheat from this as well. Okay, not this one. Okay, I couldn't cheat much anyway, so I need to find something original. Okay, so let me just build up a new data set. For example, you have a data set like this, 2, 2, 3, 4, 5, for example. What is your mod? Okay, this one is repeating more than the others, so this would be your mod. And generally, we can conclude that if you have a single, if you have some curves with single peaks, usually you can say this, like it can be either skewed to left side or to right side. For example, if you have something like this, usually your mod, this is the most repeating value, right? This would be your mod value here, and of course this one would be your mod value on the other population or other sample set. And usually your median will be located something right here, and your let's say arithmetic average will be located around here. Usually arithmetic mean, I'm sorry, should be located around here. Usually there, or most of the time, they are located like this in this type of sample distributions. Okay, all right. So far, we have seen all the location measures here. Now let's solve some examples, particularly the 1.8 and 1.12 examples from our textbook. Let's do them together to understand this a little bit better. And you can also solve lots of examples on your own later and bring them to classroom if you want to share them as well. Suppose that you have n samples, n equals 6 samples, and there are 5, 7, 2, 1, 2, and 6. This is your sample set, data set. And let's calculate our arithmetic mean for this. Okay, what is this? Plus 2 plus 1 plus 2 plus 6 over, we have 6 samples, right? And it would be what? 3.83. Good. Suppose that I assume that you have a calculator. Okay, you can. I strongly suggest you to solve these questions on your own as well. For finding the median here, first I need to order them. 2, 5, 6, and 7, right? Now they're ordered, and I have even number of samples, unfortunately, so I need to take the average of them. 2 plus 2, it would be 3.5. All right. So, and I'm curious about the mod value here. What is your mod value here? The one more repeating. So your mod will be 2. So as you see, your mod is, your arithmetic mean is this one, your median is this one, and your mod is 2. Is it, confirming this, what we wrote here? Maybe yes, maybe not. If it has a distribution like this, okay, most probably the distribution looks like this here. So it was, I forgot, what was it? This 2. Okay, so okay, that is one of the examples, just one of the examples. And of course you can be asked questions like this in the exams or homeworks or whatever as well, and you will easily solve it. Okay, we're being asked about, we are given an information about a school. We have some classrooms and number of students in them. This is from a school. Data gathered, samples taken from a school, and their average heights in that classrooms. Okay, classroom 1, classroom 2, classroom 3, and it has 30 students in it, 30 students in it, and 40 students in it, and their average heights are, oops, oh, that's very tall, right? Not that much. Okay, their height is something like this. Most probably it's a preliminary school, right? Because heights are quite low, as you see here. They're just kids. And what the question is, what is the average height of students in that school? Okay, not in classroom. So how can we solve this? No other hint given to us. Let's pause the video and solve it yourself. But it's obvious, it's pretty obvious that we are going to use weighted mean here, or x. W should be what? This times this. Okay, you multiply them. Plus. Great. See, they are put in their correct locations here, and these are coming like this. Okay, that's it. And what you do in the denominator here, of course, your total weight, and I assume that they are weights. Okay, when I add them up, you will end up with oops, that was a mistake. I'm trying to be the same with what we have in the textbook as well, because then you can study on your own later. Okay, this should be 50, I'm sorry. So the result should be what? 120 here in the denominator, because you add them up and put it right here. And since we have a calculator, our weighted, the average should be this much of weight, right? This much of, okay, this much of weight. Okay, so this is all about the weighted mean example. And okay, there can be an infinite number of examples about this topic, but we will move forward with other measures, of course. So the difference measures are another type of measure that gives us more information, because what we see about the location measures can be cannot be enough sometimes to represent how our data is spread on the x-axis, right? Let me just try to show you all of the same distributions mean the same thing here. Like, okay, we need a fresh board. Okay, now here you see your, say, frequency axis, and y-axis namely, and this one would be your x. Okay, your measurements here. So suppose that you have 3 different distributions here. One of them is this one, say. Oops, not this one. And the other one is, okay, like this one. And the other one is, for example, this one. Okay, in fact, they all have like they can have the same x, right? The same arithmetic mean here, but as you see, all of them have different shapes, in fact, depending on their the shape of the curve, right? So only location measures, like here, like on the x-axis, you see, may not be enough. You need to have an idea about the spread or shape of those distribution of data as well. That's the idea. So the first one is the range. It gives us a rough idea about the differences in data. If you remember our, let's say, oxygen level examples here, like we had some data like this, 10.8 and 12.3 and 23.3. Okay, you had these 4 values, right? What would be your range here? It's pretty straightforward. Your x max measurement, maximum measurement, minus your minimum measurement here. And what was your maximum? This was your max. And what was your minimum here? This was your min. And your range would be here 23.3 minus 10.8, which would be 12.5%. So it gives you a rough idea. Why? Because only this data and this data of the data set has been taken into consideration. Only maximum and minimum, that's it. And what about the 2 or maybe 2000 values between those minimum and maximum? Okay, you don't take them into consideration, right? So we need a maybe slightly better one, which is called the standard deviation. The standard deviation, tries to get all the data read into consideration. That's that's the idea here. And when we look at the example that when we look at an example that is based on the arm length of some people, here you see given in centimeters here, and these will be used in a textile company, for example, who produce some shirts. So they will use this data to decide on the sizes of their say shirt production. That's why they made a study like this and collected the arm length data of, for example, males, for example. That's the idea. So it means that we have how many? 25 samples here, and this one should be summarized like this in 5 categories here. These are your categories, you see, and depending on your minimum and maximum values, and these are your category middle values. Okay, this one, for example, what is it's like you have 3 and divided by 2, 1.5 you go from here, 1.5 you go from here, and it would give you 34, right? These are all your middle values, and these are the frequencies of data. I'm doing a table-based summarization here, right? I just summarized all this data here in this table and their frequencies. And this shows us how will they differ from the mean value, and what would be your arithmetic mean here. You see, this is the middle value of each category, and these are the frequencies multiplied together and added together here. See, you multiply them and add them then together here. See, like this, you multiply them and add them together here, and you divide them by the total frequency here, total samples of course, and it's 25, and you will get your arithmetic mean as 40 centimeters. Here you have this one. That's the idea. Now let me ask you a question here. Did we lose or any value here? Do we have a loss in the original data here? What do you think? Pause the video and think about it for a while. The answer is yes, because there is a slight loss in data here. When you summarize them like this, suppose that you might have 2 35s here, but you take them as this as middle value, or maybe you might have 2 33s here. Who knows? I mean, you're losing that detail, right? This is just extra information about how we lose detail when we summarize the data or make transformations between different variable types. Okay, now then we just measure how far each category is from the mean. Simple, right? By subtracting them. This one is -6 away, this category is -3 away, this category is 0 on it, okay, and this is +3, and then you have 6. And when you multiply them by the frequencies as well, like you multiply this and this together, then you will have the total deviation here, right, from the mean, total deviation from the mean here, shown here. And not surprisingly, when you add them up, you will get here 0. See, this is a problem, right? I mean, I cannot understand how my distribution is deviated, my data samples are deviated from the mean. I cannot understand this. So what I need is, I mean, just an extra step here, which could be quite useful. Just let me try to show you this. Instead of this, I use this one. This is called, okay, from I equals 1 to 5. These are your categories, right? Fi absolute value xi minus x, and you calculate them like this, right? This is called mean absolute deviation. Mean absolute deviation. Why? Because we used absolute value here. But what was this one? This one was mean deviation, right? Mean deviation only, and it didn't give us a good idea here. And then you can calculate this and it will come out like this: 12 plus 24 plus 0 plus 18 plus 18 give you 72. So this would be more meaningful, right? Since we're taking absolute values of it as well. And when we divide it by, let's say, the sample size here, and you will get mean absolute deviation here. Your mean absolute deviation would be 72 over your sample size, and it should be 2.88. That's what I'm looking for here. It's very good, and it gives me an idea about the spread, about the shape of this data curve. And do you see any problems here? Yes, we have some problems. Pause the video and think about it if you want, but it is pretty hard to do arithmetics or to do computing algorithms with the absolute value approach. It's not easy to use in a computerized manner or algorithmic manner. So what we have could be more practical. So in that sense, we use something else, which is called the sum of squares method. This you see, we also take sum of squares into consideration here. This is my class middle values. This is their frequencies. These are their deviations, see, from the mean. And these are the squares of those deviations. That's it. And when you multiply them with the frequencies as well, you will have your sum of squares. What is called the sum of squares is called this one. Your sum of squares is given here. Sum of squares are given here. That's it. And when you divide those total sum of squares by the sample size, what you get will be named as variance of this data set. And if you take the square root of this value, if it's take the square root of variance, that's what I mean, then you will have the standard deviation, which gives you an idea about the spread of this data set curve from the mean value. Okay, so your variance, square root of your variance would give you your standard deviation. That's the idea about this difference measure. Now let's try to solve an example from our textbook together, so that we will have maybe better understanding here. So we will take a look at this question here, that one, and we have some data here: 1.842, 1.494, 3.8, and 1.472, and the last one is 2.298. Okay, the question asks us to first find the arithmetic mean of this data set. And what is it? You add them up. Okay, you add, say, this is A, this is B, this is C, this is D, this is E. Okay, your A plus B plus C plus D plus E over your sample size is 5, right? Your N is 5 here, and the result would be 2.298. 1812. So this would be your x, x bar, which is your arithmetic mean, and it asks us to calculate the range here. Range, what was range? You remember? X max, your maximum data, minus x min, x max minus x min. This would be the range of your data, right? If you remember from this one, it gives us a rough idea. It gives us a rough idea on the difference of data here. It's not bad, but of course it could be better. Variance and standard distribution are much better for this purpose, but that would give you this, and it would be what? So it should be your maximum value is this one, C, and your minimum value is, I think, D, right? And it would be this, I guess, 3.228. Okay, this would be your range. And the next one is you will try to calculate the variance here. How is variance calculated? You remember? Variance. How was it calculated? You remember this one? Variance. Okay, so it is. You get the sum of squares, right? So you will get this one, a minus x square, but sum of them, b minus x square plus c minus x square plus d minus x square plus, okay, e minus x square. So you will have this divided by what? Your n equals 5, right? And your sum of squares, if you remember from the what we did a few moments before, that should give you what was it? Let me just try to show you this one. So the standard deviation, we're going for this. Your variance, square root of your variance will give you your standard deviation. That's what we're trying to do here. So we first find the variance here. Okay, we're done. Then we will just find the standard deviation here. Pretty straightforward way. Your standard deviation is square root of your variance, and it should be, just let me just cheat about the numbers here. It is 1 point this one, and when you take the square root of this number here, and you will end up with this value, would be your standard deviation. Okay, this is all about the difference measures so far, but we will see more now. Now, we have mentioned that we need good sample to make good predictions of the population we're studying with. And usually we use population, we use Greek letters for population parameters, and the mean, I mean the arithmetic mean of the your population parameter, say population parameter, is shown by mu, where it corresponds to your arithmetic mean in sample statistics, right? Sample statistics. That's how we make the distinction between them. And your population variance is depicted with this sigma square, and it also corresponds to S square in your sample statistics. And this is your arithmetic mean, and this would be your variance. That's the idea. And in order to make some predictions with sample statistics, okay, using this you're trying to predict this, using this you're trying to predict this, ideally you can never reach the total population value here, okay? It's impossible. So you will always be at least one less from the original number of people, a number of samples in that population. So that's why instead of dividing the sum of squares by n, we divide the sum of squares by n minus 1 to make it to make your sample statistics be a better predictor. And that's the idea. So what we're trying to do here results in biased or unbiased prediction. So your S square here should be 1 over n minus 1 sum of squares x minus x square. Okay, this one is a better predictor instead of this one. Okay, if you calculate your S square with this one, as we did before, a few moments before, if you do it like this, that would be a biased prediction. However, this one, however, this one should be an unbiased prediction. If you do it like this, that's the idea. So we're going to use it like this. And your S will be eventually, your standard deviation would be something always positive that we're seeking for, and it would look like this. That's the idea. If we return to our arm lengths example here, I mean, what was your, here, this one, right? Oops, I'm sorry. What was your standard deviation here? This one, right? Okay, this one. Your standard deviation was this value, right? 3.499, and it's 3.499. And if we return to our example here, your S square would be 3.499. But instead of dividing it by n, we will divide it by n minus 1, and the resultant unbiased predictor of this variance will be something I'm sorry, this should be your S. We're talking about the standard deviation here, right? So it should be square root of this one. Okay, this one. And it should be 75. and when you take the square root of this one, your S would be 3.571. Okay, this is unbiased one, and this is, see, when you compare them, this would be your biased population parameter predictor here. Okay, what we're trying to do here is, in fact, we're trying to predict this very important population parameter, your variance or rho, I mean sigma itself. We're trying to predict it by S, and we will always use this one. Don't worry. I mean, please be careful here. We will always use unbiased prediction method here, because it is mathematically and statistically the correct one. Otherwise, if we use n here, instead of n-1, we are assuming that we take all the samples in that population into consideration. Okay, so I mean, if we are curious about the average height of people who have gotten the Nobel Prize so far, and we included all of the people there, then you can use n, yes, and that would be correct. But this time, what you find as mean would not be, that would not be a statistical parameter anymore, a statistical variable anymore. It would be a population parameter directly. See, that's the idea. Only in this case you can use n. Otherwise, if you're, let's say, curious about the height of people, average height of people in Turkey, for example, and you work on, let's say, maybe 100,000 people data or something like this, you should go ahead and use n-1 to have an unbiased predictor for that population parameter. This is the distinction, and it is very important. And let's go ahead and talk about data encoding for statistical calculations. Why do we do this? The main idea is making calculations easier for us. If you have tried to solve any examples on your own so far, you might have already noticed that it is not easy to make those calculations. You need to, you would love to have some practical methods for this, and one of the most basic ones and most useful one is data encoding. Now let's see how it goes. We do this data encoding by means of addition, subtraction, multiplication, and division on the data set, on the sample set that we have. And let's take a look at how it affects the arithmetic mean, all of them. How do they affect the arithmetic mean? Now, if we, have a fresh board. Suppose that you have a variable x and we added a, for example, okay? The effect of addition we're talking. Now the coded one will look like coded data. All of the data would look like this, right? And what happens to the arithmetic mean, for example? So it would be from I to n, x plus a. So it would look like n times a. So, and if you're talking about the arithmetic mean, then we need to divide it by the number of samples, right? So 1 over n xc. So it would be simply this one plus a. See? And you know that this is already known. before. This is our classical x, right? So you can easily say that your coded arithmetic mean is plus a. So this is one of the effect of the arithmetic mean. It is the simple. It's straightforward for if you make a minus here. So it would look like this. Now, if you do a multiplicative coding here, let's see what happens. If you do a multiplicative coding here, so it would look like this, right? So this is your original data here, and this is how you code it with multiplying by a. This is what we do, and what happens here would look like this. So, oops, I'm sorry. Use white color. Your xc, sum of x coded data becomes a x, and it would look like this directly. And what would be your coded arithmetic mean? It would be 1 over xc from this definition, and it will be what? Since this one already has a, it would be a times your original x, right? Since this one is right here, you see. Let me write it explicitly if you like. Okay, so that you will understand it better, hopefully. Oops. So it is 1 over n a x this would look like this. A x. Okay, this one has already a meaning, so it would look like this. Okay, this one, your coded arithmetic mean would be this one. Okay, so let's put another color for this. And if you code it like this, then you can turn it back just by doing the inverse. So what should be your original one? You can easily come back from coded data by this one, just doing the inverse of the operation. Okay, this is how we do it. This is how we come back from it then when we finish. And the same thing applies for this one as well. You see, look, if you did this operation, then if you want to come back from the coded data later, you will use this for coming back later, and you will use this for coming back later. Now, if you do something mixed over the original data, your coded one would be like a times x plus b or something like this. Then you do this simultaneously at the same time, so it would look like this: a x plus b. Okay, I'm curious about the arithmetic mean again, and it would look like this: plus a times b, right? That's right. Oops, and we have also n of them, right? Since you have n data, AB, when you add them up, there will be n of them, right? And then your coded xc would look like this. C, and it would be a over n x plus ab, and your coded arithmetic mean would look like this: AB. Okay, and that's the idea. And if you want to come back from this value, let's use green for this one, for example. If you want to come back from this value, you do the inverse operations here, like okay, your x would be 1 over a xc minus b. This is how we extract. We're trying to extract this x from this one. Just coming back means like this. So this is what we do for coming back from this coded data. Okay, this is about the effect of arithmetic and multiplicative and mixed coding on the arithmetic mean. The effect of coding on the arithmetic mean here. Now, let's take a look at what happens when we do data encoding. Okay, when we do data encoding by addition, subtraction, or subtraction and addition are the same thing. Multiplication, division, same thing, and mixed forms. And let's take a look at what happens on the variance and standard distribution when we make coding. That would be also interesting to note it. Let's do again the straightforward additive coding first. Addition, coding by addition, like this, x plus a. Okay, now what we need is you need to find the differences from the arithmetic mean, right? This is what you're curious about, and it would look like this: x plus a minus x plus a. Is that right? Yes, we know this from we know how the coded arithmetic mean is already affected in the previous examples, so we know what it is. So the result will be minus a, these go, and the result will be x minus x. So see, it's familiar, and we can say that it is the same. Like if you have xc minus xc square would be this one directly, and your sc square would be 1 over minus 1, the total xc square here, and it would be 1 over minus 1 and minus 1, x minus square s square. So if we do additive coding here, it has no effect on the variance or standard deviation. It would be the same. Okay, so we can say that sc square equals s square, and your sc equals s. You can say this. And what happens if we do multiplicative coding here? Let's see, and it is also interesting. It means that we code it with b, for example, this time. This is your original data, and you extend it with x. What happens here is, let's try to find the bias here from the arithmetic mean coded. Be b minus x, and it should be b times x minus x this time. See, now it has a multiplication. It's not the same here. See, it was the same and it didn't have any effect, but now we have the multiplication constant here, so it can cause us some work to consider. and your xc minus xc squared, this is what we're trying to calculate. It's not easy, right? It takes some time if you use a calculator and solve some examples on your own. It would look like this, and total xc square like x minus x square, and your sc square would look like this, 1 over n minus 1, because it's unbiased, right? Why are we using n minus 1 instead of n? We already know this, right? Because what we're doing is trying to have unbiased prediction on the population parameters, and it would be what? b square 1 over n minus 1 x minus x square. Oh, good. So okay, I mean this one is already your original s square, right? So you can easily say that your sc square is b square s square. Okay, this is what you have here, and this is the coded variance here. Coded variance. If you want to come back from this coded value, you're trying to extract s from here. Your s would be what? S square would be sc square divided by b square this time, right? If you want to come back. So, and of course your s is b, sc is b s, and this is your standard deviation, right? And your s would be sc over b, not surprisingly. Okay, these would be your the effect on multiplicative coding. And now let's take a look at the effect of the mixed form here. And I think you already guessed, but the thing is, I mean, you remember that addition didn't have any effect on the variance here, right? So it's exactly what we're expecting here. It will have no effect. This part will have no effect, but this part will be exactly affecting like that. So that's the idea. So your xc minus xc would be something like this: a x plus b minus a x plus a b. Okay, like this. And the result will be ax plus a b minus a x a b. And okay, what you will have here, these gone away, and you will have a x minus x. Okay, this is it. And I won't do the same calculations again, but the idea is your sc square equals a square s square, and your s is a sc is a s. And if you want to come back from them, if you want to extract it, your s is c square divided by a square, and your s is your sc divided by a. This is how you come back from them. So these are the cases for the mixed form. So that's it. I mean, about the coding here, and we can say that they are really practical in terms of calculation. Okay, now we will take a look at some practical methods for the calculation of mean and standard deviation, because it can be tricky. Now let's take a here we will introduce something real nice, which is called our correction term. And let me show you how lovely it is. That helps us with the calculations, and you will love it, hopefully. Now, the thing is, when you're, trying to find your variance here, what we do here is like getting the total of x minus not squares, right? This is what we do. Look at this equation, okay? Now, what we're trying to extract from here is the standard deviation. In fact, we always try to find this, and this exact formula would look like this, right? And what do you think is the most time-consuming or most troublesome calculation here? Taking the square root of this value, it's pretty easy, right? In an algorithmic way, or with the computer or with the calculator, one step, right? Or dividing this number by the number of samples, okay, it's again single step, right? Very easy. But calculating this one, now, that's the tricky part. And let's see if we can have something practical for calculating this particular troublesome part of this equation here. So let's write it here explicitly, and when we do this, it would look like this. I will just distribute this square here in it. It would be x squared minus 2x, your sample and arithmetic mean, plus your arithmetic mean square here. Okay, what you have here then can be combined like this. Okay, I'm now expanding this summation over these, and it would look like this: minus 2 not x. See, I add all of these, and then the if I do this n times, since I have n samples here, that would look n x squared. Okay, this is what we have, and then we have something like this: x squared minus 2 x over n times x plus n x over n square. Oops, did I make a mistake here? No. In fact, it's a mistake. It's just I couldn't write it lovely enough. Okay, this is summation symbol here. Okay, what you have here is the square of this one. Okay, look how I come from here, right? I write this like this, and I write this. I just expanded them. Okay. Okay, and I see my mistake as well. Okay, this is not n, of course, right? This is x. Okay. Total number of the total of all, the sum of all the samples here. Okay, I go ahead and do the calculations again. Minus total of them square, right? From here over n, plus you have now, okay, this one would look like the total of them again, like this one, square over n. Can you see this? Since it would be n over n square here, you will have only n here, and this is the square of this value. Okay, when this one cancels, you will have only a single one of them here, right? You will have only a single one of them, and the equation will look like this. X squared minus total x squared over n. Now, what we did here, in order to find the arithmetic mean, we already had to do this calculation, right? We would have this number in our hands, in our pocket, and taking the square of it is nothing. Then dividing it by n is nothing. And all you need to do is find all the squares of the data and add them up together. Instead of, subtracting them all the time from the arithmetic mean and taking the squares of them again. So as you see, this one is exactly what we have here, minus square, okay? And it is much more practical to calculate, and this part of it is a name which is called the correction term, okay? This will help us to make the calculations in an easier way. Now let's try to solve an example and let's use it together. We have some babies newborns in a newborn clinic here. This example is from the book 2 plus 6, and these are their weights. This is your data set: 3.3, 2.3, 3.3, 2.8, 2.9, 3.3. Okay, what else? 2.9 again, and 3.4, 2.8, 3.7, 0.6, 3.1, 3.4, 5, 8. Okay, and you have what? 3.1, 2.6, 2, 9, and finally this one. Okay, how many babies do we have here? Since it is 5 times 5, we have 25 babies here. And let's use a coding like this. We multiply them and we get rid of the fraction part, and your XC total will look like this if you use your calculator. Of course, pause this video and please do this calculation on your own as well to understand it better. We will step by step solve some examples about this later too. Oops, what happened? Okay, I don't need a ruler at the moment. And it would look like this. And when you make inverse coding here, as if you remember, your x will be your xc over your 10 here, since you extended, and your x would be 3.004 kilograms, and this would be your arithmetic mean. Okay, you already have this one. Now let's take a look at how we calculate the standard deviation here. You remember here? Now I need this value and this value here. So the sum of squares of all of the coded variable is this one. This will take some time, I warn you. And so xc minus xc, this will of course take some time, I warn you, but the other ones are rather easier to calculate. Okay, this one, and it looked like this: 281 minus this one. You already have it, right? Like this look here, you have this, and you put it here and take the square and divide it by, you already have n as well here. You just put them in there. It's a piece of cake operation, and as long as you have a calculator, and of course you will have a calculator in the exams and all the time, and this one would look like this, and the result will be 96. Okay, now your s square, sc square, will look like this: 1 over n minus 1 xc square minus 1 over n x c square, right? And you already have this value, and since you have you already have this value calculated, right, this one, and you put them in their correct positions, and this is 1 over 24. Be careful, because we're doing what we're doing is unbiased estimation, and the result will be this one. But be careful, this is for coded values, okay? Since it is for coded values, then you need to convert it back to original values, right? This is what we're looking for, of course. But let's just try to go for it. Your s square would be 1 over 10 square, coming from the definition. The coding part that I explained to you a few moments ago. So this would be your sc square, and your result will look like this. Would be 0, 3, 7. All right. So this is your original, let's say, s square is this one. And what about your standard deviation here? Your sc square equals I'm sorry, not sc square, your sc, this one, on the coded one, and it would look like what? Your original s would be 1 over 10 times sc here. It is 3.657. Let me write this result of this square root operation, and it is 0.57. Okay, it is 3.657 divided by 10, so it would be kilograms, and this is your standard deviation. Okay, this is your standard deviation, and this is your variance. If you take the square root of this value, you will get it directly as well. Okay, and what about the coded values here? This is your coded standard deviation, and this is your coded. This was your, let's say, was for them, because we're not they are just coding to make the operations easier for us. These cannot be our results. Our results should be the red values all the time. That's the idea about the coding here. Okay, now let's solve another example from our textbook again. Like, okay, we have here the heartbeat of the almost 10,000 people here, and their all the sample data set has been summarized for us already with a table here with categories 8 points apart from each other, starting from this one, and this is the middle value of all the categories, and their frequencies are given for us here. So it's piece of cake, right? But the thing is, if you want to make an operation directly on these values, these would be rather ugly, okay? You just, for example, if you want to find the total, if you're trying to find this fi or something like this, it would be ugly, right? To multiply all these numbers together and add them together. In order to make the calculations easier for us, we will code them. With what? We will make a coding like this. It is lovely. We first subtract this number and then divide it by x. So what is going to happen to our values in this time? It would be amazing, okay? When you code all of the middle values here in this sense, you will have amazing stuff that you can calculate easily. Now what we're trying to do here is fxc should be something really comfortable, which is this value. It's piece of cake, right? You multiply this one with this one and add this one with this one and add this one with this one and add, and you add all of them and you will get this. And it would be quite efficient for calculation. Oops, what a bad writing. fxc equals, of course you will have a calculator. Just pause the video. I suggest you to pause the video and do all the calculations on your own, please. I mean the sum of all frequencies, and fxc, it is 1 over n fxc. So the result will be your arithmetic mean of coded value will be, and this would be your n, right? And your n is 9465, and the result will be 6.3. Great. Now, if you're curious about, or if you want to find the arithmetic average of original value, what you have to do is just multiply by the coded average plus this time like this, right? So it's amazing, and the result will be x 8 times 6.3 plus this value. Okay, that's the idea, and the arithmetic average will be almost 110. I think these people are patients taken from a heart clinic or something, because it's obvious that the heartbeat rate is quite higher than normal. Most probably they're being treated for tachycardia or something like this. Okay, but this is another story. Let's just write the coding here in order not to forget. It is xc equals x minus this value over 8, right? So this is how we do our coding. Now let's find the variance of coded variables, coded sample set, and it would be this, right? And this is our practical formula. This is our practical formula for calculating the variance, and it will help us a lot. C square over n. Wonderful. And this is your correction term, right? And let's try to calculate it first, and it would be, you already have this. FC is, where is it? This one. You see, you already have this, and you will put it right here. So what it would look like, it would be very beautiful. Okay, we're operating this part, and it would be your correction term. Correction term will look like numbers are big, but it's not a problem for your scientific calculators. It's not a big deal. Okay, 0.55. This is what you will get, and this one takes a bit of time, but it works. Again, it's still easy. 0 square plus 6 times 1 square plus goes and 14 times 1 times 14 square. Okay, and the result will be this one. Oops. Okay, good. This one goes right here, and this one goes right here. See? And finally, your SC square will be this one subtracted by this already calculated value here. Okay, since we have them here, you see, and divided by n minus 1, right? What was your n minus 1? It is this value, because we're trying to do an unbiased prediction. And the result will be your coded variance will be this, and your coded standard deviation will be the square root of this value, which is let me cheat. Okay, this one. Okay, this one will be your values. And how do we calculate this part? Okay, maybe this is the most boring part, but it's easy, right? I mean, again, still it's easy. What you do here is you just do this in a straightforward way. Since they are coded, it's not a big deal, okay? Okay, I'm starting from the top row, okay? 2 times because 0 square plus 6 times 1 square plus 39 times 2 square plus goes like this, plus 5 times 13 square plus 1 times 14 square. This is, I add all of these, plus I add all of them together, and this is how we do it. Okay, so are we done yet? Of course not, right? We're not done yet. One more step ahead, because those are all coded values. We have nothing to do with coded values, because we need it back to our real life. So how we do it? We do the inverse coding here. Your S square is, again, what we do is inversed here this time, C square, and it is 64 times this 2.8875. So it would be, this would be your answer to original variance. And you can either directly get the square root of this one, or go back with the statistical coding as well. It is 8 times 1.6993, and it would be 1354. Okay, this one. So this would be your standard deviation in the original value. That's it. So what you have here, but what happened to minus 59 plus 5? What happened? We don't need it in the variance part. You remember from our okay, this one, I think, right? Because it had no effect. Where is it? I forget. Because it had no effect on variance. Okay, see, it had no effect on the variance when we code by multiplication. Addition or subtraction. It had no effect on the variance. That's the only thing that had effect was the multiplicative component of the coding. That's the idea. Okay. Do you want to make the calculations even more easier? Yes, so we also have some methods for this, which is called the finger calculation method. It's pretty blunt, but it works. Like we calculate the mean, arithmetic mean, by mid-range and the standard deviation with the help of this table. We will going to use the arm length example that we discussed before in this chapter. The mid-range is pretty straightforward, okay? You take the minimum value plus maximum value in the data set divided by 2. Look, it's something very convenient, right? What is the maximum value here? This one. And what is the minimum value here? This one. You add them up and divide it by 2, always 2, and the result would be 40. Voila! I mean, is this magic or something? Like when we go back to our arm length and when we make this calculation, we get this one as well. So is this magic? No, I mean, we were just lucky. I mean, but it gives you a rough idea as long as your, distribution is close to normal or something. This type of practical methods would give you approximate results. This time it is obviously the same, but it's of course pure luck. But we were just lucky. And how about the standard deviation here? What was our standard deviation? If you remember, let's see how close we can get to this 2.499 value by using finger calculation method here for standard deviation. And this one is, you change the, difference range here. You change your range value here. What was your range value? You remember, for defining the populations, right? In the difference measures, this one, right? Your range. Okay, you just divide your range value, which was your what? Max value minus min value, not mix. Max value minus min value by 2. This is how we calculate not 2. We don't divide it by 2, but that was your range. Okay. Here we will divide this range by a value taken from this table. Okay. Now I calculate this max minus minimum and over. How many samples you have here? Just think about it. How many samples did we have here? Since we had 25 samples in this, and up to 10 samples, we will divide it by 3. And up to 30 samples, we will divide it by 4. And up to 100 samples, we divide it by 5. And if we had 35 samples here, we would divide it by 5, for example. But since it is not exceeding 30 value here, we will divide it by 4. And what was your max and min values? We already have them, right? 47 minus 32. And the result will be what? 2.5. Oh my God, is it magic or something like this? We're just getting too close, right? The original value was in fact this value. I'm sorry, the thing that I showed you before was the biased one, right? It was your biased one. This one was the biased one because it was divided by 25, right? The original one was, you can check it from your calculations, if you divide it by n minus 1 here to 24, you will end up with this value. But still we're so close. I mean, we got 3.5 here for the standard deviation here. So is this some sort of magic or something like this? No, it's not. We're lucky. We were lucky again. But this finger calculation method has some really useful use for you in the exams and while you're doing homeworks and of course in real life if you're dealing with statistics. Just imagine you're occupied with this much of numbers or something like this, 5, 3, or something, and you end up with a value, for example, like 35.12 standard deviation. Just do your finger calculation as well, which will give you 3.5, right? And you will understand that, oh my God, this is what a significant difference between the standard deviation, right? It is absurd difference. Now you can go back and understand that I think I might have done something with my standard variance calculation. Maybe my inverse data encoding is wrong. Maybe I forgot the step that I need to convert my coded data back to normal again. So this is for double checking, okay, your results, and it's pretty useful for double checking your results, okay? It's not directly for solutions, but it is pretty useful for double checking your results. And finally, the last thing that we will going to talk about is the coefficient of variance. When we're trying to compare the parameters of different populations A and B, but they're not quite relevant with each other. For example, just imagine that we're going to compare two different populations about their tail length, for example, between elephants and mouses. And your standard deviation for elephants at the, for example, tail size is, let's say, 30 centimeters. But in mouses, it will come out as 1.5 centimeters. Can you say that, I mean, this one has a wide spread or this one has a, I mean, very tight spread or something like this? It will not give you an idea, right? Because, I mean, their lengths are different as well. So that's why we need the coefficient of variance calculated with respect to your average or arithmetic mean as well. Or, for example, if you're dealing with the sugar level on the blood or urine samples, okay, which one is differing more in those samples after given a particular diabetes drug, for example, okay? So what we do here is, let me just show you the example about just we solved before, and the heartbeat. Our standard deviation was in this, our standard deviation, namely your S was what? 13.594, right? We had already calculated this. Now your coefficient of variance is the percentage that you multiply this one by and divided by what? Your average. That's it. So you have here 4 times 100 divided by your x, which was a bit high, right? You remember? When you make this calculation, you will end up with your coefficient of variance as 12 point. Now that gives me an idea. And if, for example, given a particular drug, your coefficient of variance is something like this in urine samples, for example, and it comes out that in blood serum samples the coefficient of variance is 50%, you can say that this one has a more tight spread than the this much of spread in, for example, blood samples. That's the idea for comparison, but be careful about irrelevant comparisons. I mean, if you're comparing the apple weights with, for example, tail lengths of mouses, so look, this is an irrelevant comparison, okay? It doesn't have a meaning at all. I mean, it will not help us to make irrelevant comparisons be relevant. No, it's not possible, but we should be careful about, okay, doing similar, okay, relevant comparison, like apple weights, coefficient of variance in an apple population and coefficient of variance in a, for example, watermelon population. Okay, now that makes sense, okay, since they are relevant. Making them relevant is our job. The researchers or the person who studies is responsible from this. I mean, because coefficient of variance is not something magic that can help you with any type of population comparison. Just be careful about that. Okay, this was all about the first chapter, where we made a brief start, and we discussed about the basic concepts and definitions of statistics, and I strongly suggest you to solve some examples on your own and make calculations on your own, because you will make many mistakes and learn it better while you're struggling on your own, and you will get better at understanding what is how to manipulate with that data, and how to summarize it, how to extract the descriptive, the location parameters and difference measures from that data to make a good prediction on the population parameters by means of sample statistics. Okay, thank you for listening.